Outcomes assessment for engineering education, the future. My name is Wajid Hussain, Director of the Office of Quality and Accreditation, Faculty of Engineering, Islamic University. The future of technology in engineering, medicine, law, business. Why not outcomes assessment for education? Here we go. Log into the Islamic University portal. Student, faculty, and chair profiles. Course syllabi as per OBE format with the action verbs highlighted. Lecture plans. Syllabus topics in order of OBE course formats. Grading policies. Learning management system with lessons uploaded. A digital gradebook with programmable categories and C-curving features. Multi-term course access. Faculty submitted student assignments. Tons of data. Thousands of student documents. Paper-free economic audits. Access to history is just a few clicks away. Any program is accessible, any term, any year data. Scientific constructive alignment for unique assessments with course outcomes, their performance indicators, and ABET student outcomes listed. Specific performance indicators for measuring skills in engineering courses classified per Bloom's 3 domains: cognitive, affective, and the psychomotor domains with their learning levels. 6 learning levels of the cognitive domain, 5 learning levels of the affective domain, 7 learning levels of the psychomotor domain are all measured. All of these learning levels are grouped according to the 3 skills grouping methodology. Several hundreds of performance indicators for various programs. Course exit surveys, statistical, analytical information, multi-program, multi-course, multi-term, information for faculty and course improvement efforts. John Hastell's Faculty Course Assessment Report, a structural reporting format showing course reflections, action items based on standardized headings targeting failing outcomes and performance indicators data. A list of detailed course outcomes measurements and a consolidated course outcomes plot with scientific color coding system. A summarized list of assessments mapped to their course outcomes and performance indicators and ABET student outcomes. ABET student outcomes, their key assignments, and final calculated student outcome values. A consolidated ABET student outcomes plot. 10 student outcomes measured in a single course. Performance indicators measurements, their key assignments, the EAMU values and weighted averages. Excellent, adequate, minimal, unsatisfactory. And finally, a consolidated PI's plot. The analytical FCAR with measured course outcomes, their key assignments, and detailed student performances showing the EAMU color-coded categories. An excellent tool for real-time formative assessment of course delivery. Term-wise program evaluations showing measured ABET student outcomes and their performance indicators, with the capability to zone into failing performance indicators information, in-depth root cause analysis, activate edit mode to view details from contributing courses, evaluate course FCARs, faculty action items, allocate and transfer action items that are scope of the program and not of the faculty. Each individual student's performance analysis based on ABET student outcomes, assessments, and PI's information. 17 standing committees communicate with each other using the CIMS system. Electronic documentation of meeting minutes, action items for EC evaluator access. Standardized meeting minute templates and task lists for all committees. Now let's take a look into the Faculty of Engineering, Islamic University Outcomes Assessment Model. Course outcomes measured for all courses in the program curriculum using specific PIs related to ABET SOs involving faculty each term. Specific PIs comprehensive review involving faculty every 3 years. 11 ABET SOs comprehensive review involving faculty every 3 years. And the program educational objectives comprehensive review every 5 years. The 3-level skills grouping methodology of Bloom's revised taxonomy, grouping learning levels of the cognitive, affective, and psychomotor domains into elementary, intermediate, and advanced skills categories. The design flow for the creation of advanced, intermediate, and elementary COs, PIs covering 3 domains of Bloom's taxonomy and spanning courses in different phases of the curriculum. In an ideal situation, introductory level courses should have a high percentage of elementary skills and a low percentage of advanced skills, whereas mastery level courses should have a high percentage of advanced skills and a low percentage of elementary skills. An ideal learning level distribution scenario for introductory and master level courses indicated by shaded red and blue triangles. A hypothetical relevance and coverage of ABET student outcomes to Bloom's 3 learning domains. Student outcome A, an ability to apply knowledge of math, science, and engineering, high cognitive, low affective, and low psychomotor. Due to the maturity of skills attained by students in the coverage of various learning domains, different types of assessments have to be weighted. Now, 4 course formats were developed by the Faculty of Engineering to calculate multiplication factors based on course grading scales for estimating the weights for different types of assessments. In this example, final exam question 1, 15 points out of 100, so 4.5% on the course grading scale multiplied by 8 multiplication factor from course format 2 gives us 36% weighting factor, which is greater than the weighting factors for midterm exams, quizzes, or homeworks. EAMU performance criteria: excellent 90 to 100%, adequate 75 to 90%, minimal 60 to 75%, unsatisfactory 0 to 60%. Heuristic rules per PPT tables: red flag average below 3.3 and failures greater than 10%, yellow flag average below 3.3 or failures greater than 10%, green flag average greater than equal to 4.6 and no failures, and no flag, none of the above. In the given table is shown an example of how EAMU vectors are computed for a specific performance indicator. Assessments homework 3 and homework 8 are selected for measuring a specific PI, ABET PI 5-3. In this example, there are 7 students with scores corresponding to homework 3 and homework 8. These assessments are rated according to course grading policies and multiplication factors. Let's say the weights are 5% for homework 3 and 7% for homework 8. We calculate new scores for homework 3 and homework 8 based on the assigned weights and then add them together to calculate the percent weighted score, which is 66.67 for student 1 as in the given formula. The PI EAMU classification for each student in the class as indicated in the second column is obtained from this percent weighted average. The PI EAMU vector 3112 for the entire class in the last column is obtained based on the count of students belonging to each of the categories as defined by excellent, adequate, minimum, and unsatisfactory. In this case, there are 3 students with scores belonging to E, 1 in A, 1 in M, 2 in U categories. Finally, the weighted average of the EMU vector for this specific PI 5 is 2.86, which is obtained as per the equation shown. EvalTools calculates the EMU average reading by rescaling to 5 for a weighted average based on 3-point scale as shown in the equation. An example of a civil engineering course showing CO2 described the composition of soil and soil volume mass relationship equations for soils, and ABET PI 534 determined the physical properties of soil using given parameters. They are measured with assessment midterm 1 question 9 and assigned to the intermediate cognitive applied skill level based on the 3-level skills grouping methodology. Example of an electrical engineering course, electric circuits showing CO4 apply voltage and current division rules appropriately to solve simple circuits using midterm exam 1 question 3 for theoretical skills assessment and lab report 3 for practical lab work skills assessment. Now PI 218 is measuring practical skills using lab report 3 and related to the ABET SOB and ability to conduct experiments, and ABET PI 519 measuring theoretical skills using midterm exam 1 question 3 related to ABET SOE and ability to solve problems. Coming to learning domains. The cognitive domain involves acquiring factual, conceptual knowledge dealing with remembering facts and understanding core concepts. Procedural and metacognitive knowledge deal essentially with problem solving, which include problem identification, critical thinking, and metacognitive reflection. Remembering facts, understanding concepts, and problem solving are essential, core, and universal cognitive skills that would apply to all learning domains. To successfully complete psychomotor tasks for solving problems involves acquiring very specialized portions of factual, conceptual, procedural, and metacognitive knowledge of various physical processes with accepted levels of their skills proficiency. Similarly, in the affective learning domain, activities such as implementing a code of professional ethics involves acquiring factual, conceptual, procedural, and metacognitive knowledge relating to industry standards, process of application, level of personal responsibility, and impact on stakeholders. The learning domains wheel was implemented with Venn diagrams to represent details of the relationship of popular learning domains categories, interpersonal skills, and types of knowledge, and was developed by the Faculty of Engineering to analyze the popular learning domains models available, including Bloom's, with the perspective of realistic measurement of outcomes based on Ralph PI's classification. Essentially, the psychomotor and affective domain skills overlap with the cognitive domain for the necessary factual, conceptual, procedural, and metacognitive areas of knowledge. The learning domains categories such as interpersonal, IT, knowledge, cognitive, communication, numeric skills exhibit significant areas of overlap as shown in the learning domains wheel. Now, crucial guidelines were logically derived from the learning domains wheel for the selection of learning domains categories. The most critical was to avoid selection of any two skill sets as learning domains categories when one is an absolute subset of another. Just select either the most relevant one or the one which is a whole set. For example, select cognitive or numeric skills, but not both. The philosophy behind the implementation of the hierarchy frequency weighting factor scheme for engineering program learning domains evaluations is to holistically measure all skill levels in all course levels in all three Bloom's learning domains while giving prevalence to higher order skills over lower order skills and considering the counts of assessments implemented in each learning level. Learning domains evaluation for electrical engineering program term 361 showing all three domains composite data with assessment counts labeled N and their aggregate average values for various learning levels for all 11 ABET SOs. ABET SOA is highlighted showing 51 assessments processed in term 361. In the OBE model, assessments are equivalent to learning. Therefore, learning distributions for all learning levels are computed based on the percentage of total assessments processed in a given term for a specific learning level. A point to note, since mastery level courses were not offered at the time of this research, this data contains information from just the introductory and reinforced courses. Weighting factors for the various measured learning levels for ABET SOA are calculated by multiplying multiplying learning distribution values with relative distribution values, thus giving higher weightage to higher order skills, advanced course levels, and learning levels with greater counts of process assessments. Please note introductory intermediate level weighting factor is 62.45. Now the ABET PI 112 Bloom's learning level cognitive intermediate applying measured in an introductory level course circuit theory has a weighting factor 62.45. All PIs measured in term 361 for electrical engineering program are accordingly weighted averaged as per the shown equation to get the final average value of 2.5 for ABET SOA. The individual learning domain analytics show assessment counts, averages, and learning distribution values for ABET SOs A through K for all the three learning domains of Bloom's taxonomy. Learning domains evaluation histograms and pie charts for engineering programs term 361 show percentage distribution of assessment activities in Bloom's three learning domains. Any deficiencies in holistic coverage of three Bloom's learning domains, all course levels, all skills levels for various ABET SOs are easily identified to help create action items in program evaluations for future improvements. Course level learning domain coverages are also implemented at the Faculty of Engineering to indicate real-time deficiencies in course deliveries. The Faculty of Engineering at Islamic University has successfully implemented groundbreaking digital technology and world-class outcome-based education methodologies to sophisticate and streamline its efforts for both CQI as well as accreditation. We would like to thank you very much for joining this presentation. Goodbye.